this video, we'll talk through the Advanced Higher Chemistry Unit 1 topic of acids and bases. By the end of this video, you should be able to describe the behaviours of acids and bases using the Brønsted-Lowry theory and also be able to identify the conjugate pairs. You should be able to calculate different values to do with acids and bases, including pH, pOH, Kw, Ka, and pKa and pH of weak acids, salts, and buffers. You should also be able to explain how equilibrium explains the behaviours of strong and weak acids and bases and the formation of salt solutions, buffers, and indicators. Starting off with ionisation of water when water splits up into ions. At Advanced Higher, we're going to use H3O positive, which is a hydronium ion. The shorthand of that would be the H plus ion, the hydrogen ion that you should be familiar with from previous courses. In water, there is an equilibrium between water molecules and the hydronium and hydroxide ions. That gets represented as water plus water. It's going to make hydronium and hydroxide. The simplified version that you will be perhaps more familiar with is H2O splits into H plus and OH minus. Value that's very important in this topic is the ionic product. This is an equilibrium constant, the same as in the equilibrium topic, where we work it out by doing the concentrations of the products divided by the concentrations of the reactants. As in that topic, if you have a liquid, it's given a value of 1. Similar to in the equilibrium topic, if you have any liquids, they are given a value of 1, which in this case would just cancel away. Like other equilibrium constants, it is temperature dependent, and in the data booklet, they give you the value for water at 25 degrees Celsius. The reason that we focus in on the hydronium ion concentrations is they are linked with pH by the relationship pH equals minus log to the base 10 of the concentration of hydronium ions. You'll find that in the data booklet. Some questions will ask you to work out the concentration of hydronium ions when given the pH. That's going to be 10 to the power of minus pH. In these first example questions, the values we're using are quite straightforward. Here we're asked to calculate the pH of 0.001 mole per litre hydrochloric acid. An important thing here is the formula tells us that there's one H plus in a HCl. Therefore, your concentration of hydronium ions will be the same as the concentration of the chemical. We can plug that into our pH equals minus log to the base 10 of that value, and that gives us a pH of 3. If you're asked to deal with sulfuric acid, an important thing here is that each sulfuric acid has 2 hydrogen ions in them. That means we have to double up the concentration of the chemical. So we're going to be using 0.002 moles per litre in our calculation, minus log to the base 10 of that, and the calculator tells us 2.7. There is also a relationship for the hydroxide ion concentration and the pOH. That is minus log to the base 10 of the concentration of hydroxide ions. If we're asked to work backwards, it would be 10 to the power. And here we're asked for the pH of this chemical. We are told information about the OH minus. There is one hydroxide ion within it. That means it's going to be that concentration we're going to use. We could approach it with the ionic product, where Kw equals the concentration of hydronium times by the concentration of hydroxide. We know that for water, it's going to be 10 to the power minus 14. And then if we rearrange it to figure out what hydronium is, we will end up with 10 to the power of minus 11. Plug that into pH equals minus log to the base 10. Of that value gives you an answer of 11. My preferred method though, I would change my OH minus concentration into pOH first of all. So minus log to the base 10 of 0.001 is a value of 3. And pH plus pOH is going to equal 14. 14 take away 3 gives you your 11 as well. Just for me, a bit more straightforward. Similar to the acids, if you have a chemical like calcium hydroxide, whose formula is Ca brackets OH2, there are 2 hydroxide ions. Therefore, we have to double up the concentration given. And would then plug that into minus log to the base 10 of that. That will give us an answer of 1.51. And then pH plus pOH is 14. The 14 take away 1.51, and that will give us 12.49 as the answer there. The definition that we focus on at Advanced Higher is the Brønsted-Lowry definition, which states that an acid is a substance which donates a proton, and a base is a substance which accepts a proton. When you're looking at the formulas, what you're looking for is that the acid will lose a H positive, and the base will gain that H positive. In these ones, we're dealing with aqueous solutions. That means that the H plus would join onto a water to make the hydronium ion, H3O positive. Equations will show either or, depending on how detailed it's going. I've tried to stick as much as possible to using the H3O positive. And my reason for that is on page 14 of the data booklet. They have equations for different acids breaking apart. And all these ones, they're using the H3O positive. So I'm trying to stick with that as much as I can. This would be the general equation for acids dissolving in water and splitting up into your hydronium ions, and in this case that is A-. The descriptions we use, we've got acid and base. The chemicals that they then form are the conjugate acid and the conjugate base. The conjugate acid is the species made when the base has accepted the proton, and conjugate bases are the species left when the acids donate the proton. Similarly for bases, we have our base added to water. We're going to form our conjugate base and our conjugate acid. So the B has gained the hydrogen to become BH positive. That's going to be your conjugate acid. And then the water is acting as an acid. It's going to lose a H, and then it's going to be OH minus for the conjugate base. So it kind of flips over as it goes. Some chemicals like water are described as being amphoteric because it can react as both a base or an acid. It's capable of donating or accepting protons. In chemistry, strong and weak are not referring to differences in concentration. They are talking about their dissociation, how much they split up into ions when added to water. Strong acids completely dissociate. Examples include hydrochloric acid, sulfuric acid, and nitric acid. In all three cases, it's a single arrow showing that this is an irreversible change. When it comes to weak acids, they only partially dissociate when added to water. Things like ethanoic acid and sulfurous acid would be examples of those. Those are the ones that appear on page 14. It's not an exhaustive list, but most of the questions will deal with ones that will be found in here. If we're describing about their concentration, dilute and concentrated would be the terms that I would want to use for those. So 0.1 is dilute, 4 moles per litre is concentrated, but hydrochloric acid is strong acid, and ethanoic acid would be a weak acid. When comparing strong and weak acids, if you're using the same number of moles, if you have the same concentration and volume of those, the strong acid will have a lower pH. They will conduct electricity better because there's more ions dissolved in the solution, and they will react faster with metals and other chemicals. When it comes to doing titrations, the volume that you'd need to neutralise an alkali will be identical, regardless if it's a strong or weak acid. Strong acids, they've released all of their hydrogen ions, which have joined onto the water to form hydronium. These are all freely available to react with a base in a neutralisation reaction. In the weak ones, only some of their hydrogen ions forming hydronium ions have been released. When we add a base, the OH negative will react with the hydronium ions to form water. This means that the equilibrium of the weak acid would shift to the right to replace it. More of that acid is dissociating to replace it. And that will continue up until all of the molecules of the acid are used up. So it will react more slowly, but it will get to the same endpoint. You'll require the same number of moles as you did for the strong acid. Bases, same idea. Strong bases will completely dissociate, and then weak bases partially dissociate. Ammonia is a really good example of a weak base, probably the most common one that would get picked. We have a couple of them at the bottom of page 14, and that can help guide you with what to write. When you're comparing them, your strong bases would have a higher pH, they would have a higher conductivity and a faster reaction. But in the same way, you would have the same number of moles needed to react with an acid, because strong bases have all their hydroxide ions released, which are available to react. The weak bases will only release some of them. You add an acid, that will remove the hydroxide ions from the solution, and then the equilibrium would then shift to the right to replace those OH minuses, and this will continue until you use up all of your base. Moving on, there is a dissociation constant for weak acids, which is Ka. This is a measure of the strength of an acid. The higher the value of Ka, the more split up, the more dissociated it is, the stronger the acid. They can also be represented by their pKa value, and to calculate that, we do minus log to the base 10 of their Ka, of their acid dissociation constant, and as Ka increases, pKa decreases. We can get these values on page 14, And questions might ask you to compare the values of two different chemicals. For me, I prefer working with the Ka because Ka is a measure of how far it's split. Strong acids would split completely, they dissociate fully. So the larger the Ka, the larger the Ka, the stronger the acid. And then because we're doing minus log to the base 10 of the Ka, the pK then is the opposite way around. So the lower the pKa, the stronger the acid. If we are given the value of Ka, we can work out or know how strong the conjugate base would need to be. The Ka times the Kb would equal the ionic product, the Kw. At 25 degrees, the ionic product is 1.01 times 10 to the power of 14. If you have a stronger acid, you're going to have a large Ka. That means you must have a small Kb. Otherwise, it would be more basic than acidic. And then the other way around, a very weak acid would have a higher conjugate base value. That means you'd have a larger Kb. When it comes to working out the dissociation constants, we can go back to our general dissociation for, in this case, the weak acid. And it's going to be the products over the reactants. So for phosphoric acid, we can look in the data booklet. And then what we want to do is take the two products, so the things on the right-hand side of the equation, and put them over the reactants. Water has a value of 1, so it's going to get ignored. So I've just then removed the water from the equation because it's always just going to be 1 in these questions. And it gives you the value of 6.9 times 10 to the minus 3. Benzoic acid, we'd go and find it. Higher up, go find it. Same again, products over reactants, ignoring the water because that would give a value of 1. And it is 6.3 times 10 to the minus 5. And if the question asks you which of these is the stronger acid, higher Ka, phosphoric acid has a higher value than benzoic acid. So watch for your powers and make sure you're including them in what you're looking at. When it comes to working out the pH of a weak acid, for weak acids that give up 1 proton, we use pH equals half pKa minus half log to the base 10 of C. And C is the initial concentration of that acid. So they might just straight up ask you, here is a weak acid, what's the pH? So half pKa minus half log of C. We would look in the data booklet. The pKa is 4.83, and then we're told it's 0.01. That gives you 3.42 as the pH. The question might give you a pH and ask you to work out the molar concentration. Starting off with the same relationship, we're going to do some moving around. The half log to the base 10 of C, move it to the left, make it become positive, and then move the pH over, and then take that away from the half pKa. That gives us the half log to the base 10 of C equals the half of pKa minus the pH. Getting rid of the half in front of the log to the base 10, go times both sides by 2. At this point, I think just plug the numbers in. That's going to give us what the right-hand side is. So 4.76 from the data booklet, and then it tells you the pH is 2.5. When we do that, and then to get C on its own, it's log to the base 10 at the moment. The inverse of that is 10 to the power of. It'll be 10 to the power of whatever 4.76 minus 2.5 equals. So that is minus 0.24. And then plugging it in, 0.575 moles per litre as our final answer. Okay, now we're going to look at some exam style questions. I'll talk through how I would approach each of them. We're asked about what role the HCN is doing. Right, what's happening to it? So if you watch what's happening, it has become Cn minus. It's lost or donated a hydrogen. That means it's going to be our acid. The water is acting as a base because it's accepting the hydrogen and becoming the H3O positive. And then the H3O positive would be the conjugate acid, Cn minus conjugate base, which gives us the answer of A for that question. In this one, similar again, but we're now focusing on the conjugate parts. Well, the conjugate base is formed after the acid donates a hydrogen. So we've got two NH3s. So when it loses a hydrogen, it's going to become NH2 negative. So that's going to be our conjugate base for that one. And the conjugate acid is formed after the base accepts the hydrogen. So again, the other NH3 is acting as a base. Add on a H, NH4 positive would be your conjugate base. And that should give us an answer of D for the correct answer to this one. Next one, we're talking about different values for ethanoic acid solution. Ethanoic acid is a weak acid. If you add water to an acid, it's going to increase the pH. It's going to go towards 7, up towards 7, so it's not going to be that one. pKa is minus log to the base 10 of the dissociation constant. It's temperature dependent, not anything else, so that's not looking correct. The concentration of hydronium ions, well, when you add water, it's going to decrease the concentration. It's going to become less acidic, so that all sounds good to me. When you add more water, more of the substance will dissociate, it will break apart, more of it will dissociate. That makes the correct answer C for that one. Okay, another wordy one here. We're told 4 different statements, and one of them is untrue. So first thing, hydrochloric acid is HCl. Well, HCl is a strong acid. That means it would fully dissociate, and it has 1 hydrogen ion in it. That means that is going to be correct. If it's H2SO4, you need to double it, so it's not that. In this one, we're asked about a neutralization. We'd need to think about a balanced equation. And in a balanced equation, it's a 1-to-1 ratio. Same number of moles because the concentration of volumes are identical. That would be true, not our answer. Next one, pH of a strong acid is lower than the pH of a weak acid. Well, that is incorrect because a strong acid has fully dissociated. That means all the H positives have been released. That means you have more hydronium ions, H3O positive. So that is true. And then the last one, the Ka, so the dissociation constant of a weak acid is bigger than a strong acid. That's incorrect because a strong acid has fully dissociated. And that makes our correct answer D for that one. So it's just about taking our time, working our way through those. And next question, we're asked about a weak acid and asked to calculate the pH of a weak acid. We're going to use pH equals half pKa minus half log to the base 10 of C. Find it in the data booklet. 4.87 is the pKa. That means when we plug it in, pH equals a half of 4.87. Take away half of log to the base 10 of 0.1. Popping it all in gives you 2.94 for the pH. And this one, they want the equation for a dissociation of a weak acid. This is not one you expect to be familiar with, but what we need to remember is that the acid is going to lose a hydrogen, which will be collected by the water. So it's the carboxyl group that's going to be important. It's going to be this hydrogen that is going to be moving away, and it's going to form hydronium ions. We're trying to, as best we can, mimic what's happening here. In all these cases, a H has been lost. The O of the OH is now a negative, and then you get your H3O positive. So it should, hopefully, be something like this. I just knocked off that hydrogen off the carboxyl group, make it negatively charged, and then that hydrogen has been picked up by the water acting as a base, and then that's making your H3O positive like so. The follow-up to that question is it's asking us for the concentration, giving us the Ka value of it. Now, the calculation we use involves pKa, not K. So the first thing I think we should do is to turn Ka into pK by doing minus log to the base 10 of it. Popping those values in gives us 4.85. That then frees up. That then allows us to use pH equals half pKa minus half log to the base 10 of C. So doing some moving around, we get to a value for pKa minus 2pH. And then we want to take 10 to the power of whatever that value was. And then the calculator will tell us that is 0.002 with a wee bit of rounding for that one. You can do it all in one go. There might be other ways you prefer to rearrange it, but that would be the answer we'd get. Salts are produced during neutralization reactions. The general reaction is acid plus base makes salt and water. If your base was a metal carbonate, you'd also make carbon dioxide. We're going to focus on the metal salt though. That's the main part we're asked about in advanced chemistry. The different combinations of acid and bases produce different salts. If you have things like hydrochloric, that would make chloride, sulfuric, sulfate, nitric, nitrate. Sulfurous produces sulfite. That's one that's quite commonly used because of the potential confusion with sulfuric and sulfurous. Carbonic would make carbonate salts, and alkanoic acids make alkanoates. That would be like ethanoic acid making ethanoate. Again, quite common to use. The pH of the salt solution depends on which acids and bases you use. A strong acid and a strong alkali will make a neutral salt. If you've got weak acid and weak alkali, you'd make a neutral salt as well. Strong acid, weak alkali, acidic salt. Weak acid, strong alkali would make a basic salt. Some examples would be calcium ethanoate. You would need to be able to recognise that it's calcium hydroxide and ethanoic acid. That's strong base, weak acid. That's going to make a basic salt. Sodium sulfate would be sodium hydroxide and sulfuric acid. Strong and strong makes a neutral salt. Ammonium nitrate would be ammonia, which is weak base, and nitric acid, which is a strong acid. That's going to give you an acidic salt. When it comes to explaining why these different types of salt give you different pHs, we're going to explain why different salts have different pHs when in solution. We're going to deal with ammonium chloride having a pH lower than 7. So that's going to be an acidic salt. Well, the first thing that's going to happen is that the chemicals are going to split apart. You're going to have your ammonium and your chloride ions. Now that ammonium is the conjugate acid of the weak base, ammonia. So NH3 has gained a H and it's become NH4 positive. We can use the data booklet. So down at the bottom, this is what's happening. We're going from left to right, and we're going to take our water is going to react with that ammonium ion. And as a result of this, we end up with more hydronium. That's going to increase the concentration of hydronium. That's going to make the solution acidic with a pH lower than 7. This setup works for any acidic salt. You just have to swap out the names and the ions for the relevant one depending on the question. When it comes to basic ones, it's a little bit different. Here we're dealing with sodium carbonate. Well, in water, that's going to split apart into Na positive and CO3 to negative. I've got here. So the water is going to react with the carbonate. It's going to form the H3O minus and crucially the OH negative hydroxide ions. That increases hydroxide ion concentration. That's going to make it a basic solution. The pH would be greater than 7. And then again, you can just sub in whatever chemicals you are dealing with in a particular question. Speaking of questions, here are some exam style questions. We want the lowest pH. That's a strong acid, weak alkali. A is potassium hydroxide, hydrochloric. That's strong and strong, going to be neutral, not our answer. Potassium is still strong. Potassium hydroxide is strong. Ethanoic acid, weak. Strong and weak is going to be basic, not our answer. We've got a weak base and a strong acid. That is going to have a pH less than 7. So C's looking good. And the last one is weak and weak. That's going to have a pH of 7, so not our answer. And that gives C as the correct answer there. In this one, they're asking us to explain why this chemical has a pH greater than 7. That's going to make it a basic salt. So we want to make sure our answer explains why it's basic. Well, the first thing that happens is those things split apart. So it's sodium and the 4-hydroxybenzoate ions. We're going to react it with water. The water is going to give up one of its hydrogens to that bit on the left, the conjugate base, which is going to become the weak acid. So I'm going to replace that and make it back into the carboxyl group. And when we do that, that leaves you with excess hydroxide. Hydroxide ion concentration is increased. Basic solution, pH greater than 7. When it comes to indicators, they are weak acids that change colour depending on the pH of the solution. Equilibrium set up like so. The weak acid on the left and the conjugate base must have different colours for them to work. Some examples of indicators, common ones that are used would be things like phenolphthalein and methyl orange. When it comes to working out a dissociation constant, Kin is calculated using the hydronium ion concentration, the conjugate base, the In minus, over the HIN. The colour change will happen when the acid and conjugate base concentrations are equal. That simplifies the relationship down to Kin equals the hydronium ion concentration. It can often be more helpful to work out the pKin using minus log to the base 10 of the hydronium ion concentration. And then the pH range at which the colour change will happen can be calculated by doing the pKin plus or minus 1, which again is in the data booklet. Titration curves are graphs that are plotted by adding an acid or a base during a titration and measuring the pH as it's added. At the point where the acid and alkali have reacted exactly is described as being the equivalence point. On the graphs, how you recognise it, it's the centre of the vertical section of the curve, and then the pH of that equivalence point in a titration depends on which acids and alkalis you use. Goes back to the salt that's produced. So weak acid, strong base would have a pH above 7. So your equivalence point will be above 7 in the graph. Here are the different graphs that you can get. And the green line is trying to represent the midpoint of the vertical sections. And it follows the same descriptions as the salts did. As a reminder, that's what we're looking for. 3 of the curves, there is quite a steep change in pH. Weak alkali and weak acid, it's quite a narrow band. In the first 3, it's quite easy to find an indicator that will change in that section. The weak alkali and weak acid one, there's not really that steep and pH change. It's difficult to get a clear endpoint. When it comes to picking your indicators, you want to try and make sure that the pH change range at least cover the equivalence point. Ideally, it would be as close to the equivalence point as possible. And what that means is when you add, you're slowly adding your drops of, in this case, alkali. You'll get that sharp colour change from just adding 1 drop. In this one, we're asked about which indicator should be used in this titration. It's strong alkali, weak acid. So we're looking for something that gives a colour change above pH 7. Here are the values from the data booklet. Part of bromothymol blue's range is above pH 7, but phenolphthalein has all of the range above pH 7. That would be the best indicator to use for that one. They can also ask you to work out the pH range given the KIN. We want to turn that into pKin by taking minus log to the base 10 of the value. That gives us 5.92. And then pH equals the pKin plus or minus 1. So knock down 1, gives you to 4.92, add 1, 6.9. Our last section is about buffer solutions. These are solutions that can keep their pH basically constant when you add small quantities of acid or base, or when you dilute it with water. And to work as a buffer, you need to, for a solution to act as a buffer, it must contain things that could remove extra hydronium ions or extra hydroxide ions. If you don't have these species, then the pH would change significantly. Acid buffers are made from a weak acid and one of its salts, because the salts contain the conjugate base. An acidic buffer would have a pH less than 7. And a basic buffer is made from a weak base and one of its salts, because that would contain the conjugate acid, and that will have a pH greater than 7. So an example acidic buffer would be ethanoic acid and sodium ethanoate. And then the key equilibrium is that we've got our weak acid is able to dissociate, and we've also got the salt would break apart, and it would produce more of the conjugate base. So you'll see that the CH3COO minus is in both of these equations. This means that it's got a reservoir, it's got a store of both the weak acid and the conjugate base. How do they work then? So same equations, but we are now going to add a base. Now base will increase the concentration of OH minus, which would remove the hydronium ions from the weak acid equilibrium. So up in here. And if you remove from the right hand side, the equilibrium will shift to the right. More of the weak acid will dissociate. That replaces the H3O positive, and the pH remains almost constant. It only works up to a point if you kept adding more and more OH negatives, more and more alkali. It would exhaust the reservoir, it would exhaust the weak acid, and then the pH would change. On the other side, if we're adding an acid, the concentration of hydronium ions increases. And then what has to happen then is, well, the equilibrium would shift to the left. CH3COO negative, the conjugate base, would react with it to form more of the weak acid. So it's able to remove the excess hydronium ions and forms more of the weak acid, keeping the pH constant. Again, there's only so much it can cope with. So if there's large volumes, it wouldn't work, but that's what we do for those ones. In basic ones, we have weak base and the salt of that base. We've got our equilibrium again, and we've also got the salt fully dissociates and splits up. And you'll see there that the NH3 positive ammonium is common to both of them. So you've got the weak base and the conjugate acid ready to join on to different chemicals. Right, so what's going to happen? So when we add base, the concentration of OH negative is going to increase. If we have an increase on the right, the equilibrium will shift to the left. We're going to make more of the weak base. That's going to bring back down the concentration of OH minus, preventing a pH change with small volumes of it. That's going to keep your pH basically constant. When you add an acid, you're adding more H3O positive. In this situation, the weak base would react in a neutralization reaction with the hydronium ions. That's going to form ammonium and water. That's going to then keep the pH almost constant, stopping the pH from decreasing as it would have. If you're asked to work out the pH of an acidic buffer, we do pKa minus log to base 10 of the acid to salt ratio. So an example might be one like this, where we're asked to do that for 1 mole per litre methanoic acid and 1.78 mole per litre sodium methanoate. Methanoic acid has a pKa of 3.75, so it'll be that takeaway, log to base 10 of the acid over the salt. Plugging that in gives you a value of 4, just as straightforward as that. Importance of buffers is they maintain stable pH in systems where small changes could be very harmful. Things like in the blood's pH is approximately 7.4. This is controlled by the carbon dioxide and hydrogen carbonate equilibrium. This is when the breathing out carbon dioxide, and then also the kidneys are involved in dealing with that as well. In seawater, there are chemicals that are able to take in any excess hydroxide ions or hydronium ions, because a lot of the marine life need a quite tight band of pH to survive. So now on to some of the exam style questions. We're asked which would not be suitable as a buffer solution. They're all acids, so we're looking for a weak acid and its salt. And if you look at the names of them, they're all matching. So boric, borate, nitric, etc. They all work, okay? So that then means one of these then won't be a weak acid. Now, on page 14, they have the list of some of the weak acids that we might be asked about. Boric is there, propanoic, yes, and benzoic. All three of them are. Nitric acid is a strong acid. So if you remember that, nitric, hydrochloric, and sulfuric, you can get to the answer straight away. Data booklet's there to help us out if we need it. That means B is incorrect because it's not a weak acid. In this question, we are told some information about what's going into the buffer solution, and we have to work out the pH. First thing we would want to do, I would say, is work out the concentration of sodium propanoate using concentration equals number of moles over volume. It's going to be 0.2 over 0.1 because it should be in litres, not in centimetres cubed as given. That gives you a concentration of 2 moles per litre. We can then go straight to pKa minus log to base 10 of the ratio of acid to salt. Make sure I put it in the right way. That's going to be 0.1 over 2. Plug it into the calculator, spits out 6.17 as my answer there. So you can't put the moles in this question. We want to turn it into concentration to then put it into the relationship. In this question, we're given information about an acidic buffer. And we're asked, first of all, to calculate the concentration of potassium ions in the buffer solution. Right, now we are told a starting concentration, which is 1 mole per litre. Potassium hydroxide is KOH. Both have a valency of 1, so it's going to be just one of them in there. But what we need to watch for is we're mixing them together, which means the total volume is going to be bigger than what we've started with. So because we're going from 20 centimetres cubed to 60 centimetres cubed, the diluted concentration will be a third of the original, because it's now 1 part potassium hydroxide, 2 parts ethanoic acid. So we would go from 1 mole per litre down to 0.333. Another way you could do it, you could go through the number of moles, concentrations, and volumes. So we could work out the number of moles in the 20 centimetres cubed of 1 mole per litre. That'd be 0.02. And then the new volume is now going to be 60 in the mixture. So now divide that number of moles by 0.06. And that gives you the same answer of 0.333. Depends very much on which one you prefer. I much prefer that it's a third, the concentration thirds. I just think that's a bit easier to deal with. And then they're asking us to work out the concentration of the hydronium ions in that buffer solution. So we've worked out the concentration of the salt, 0.33. We'd want to think of a similar thing for the ethanoic acid, but this time it's going from 40 to 60. It'll be 2/3 of the original value. If you wanted to, you could do the NCV a couple of times if you want, but it will be 2/3 of what it started with because it's 40 out of 60 that we've got in that case. Plugging the numbers into the relationship, we would then get that the pH is 4.46. They're not asking you for that, they're asking you for the hydronium ion concentration. So we want to rearrange the pH equals minus log to the base 10 of hydronium ion concentration. So it's going to be 10 to the power of minus pH, 10 to the power of 4.46, which my calculator says is 3.47 times 10 to the minus 5 moles per litre. And in this question, we're asked how it would work and why would it resist a change if more alkali was added. Well, when a few drops of the hydroxide is added, that's going to remove H3O positive from the solution in a neutralization. And then what's going to happen is more ethanoic acid dissociates to replace the neutralized hydronium ions for that. And that would keep the pH constant or fairly constant. That brings us to the end of the video. Hopefully you are more comfortable in describing acid-base behaviour using Brønsted-Lowry theory and also being able to identify conjugate pairs, being able to calculate pH, pOH, Kw, Ka, pKa, and the pH of weak acids, salts, and buffers, and also explaining how equilibria accounts for the behaviour of strong and weak acids and bases, salt solutions, buffers, and indicators. Thanks for watching. Goodbye.